Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the most awesome stuff. This is the AAS Journal Author Series. And I am very happy to have Joe Silber and Parker Fagrelius with us today. Hey, Parker. Hey, Joe.
Hello.
Howdy.
And Parker, where are you located at?
I am here in Tucson, Arizona.
Oh, it must be lots of snow there in Tucson at this time of year.
There's some snow on top of the hills surrounding town right now. Yeah.
Well, we're not too much warmer, about 90 miles north of you here in Phoenix, so all good. And Joe, where are you located at?
I'm in Manhattan under the long shadow of the Empire State Building.
Are you really?
Yep.
I thought you were in California.
Yeah, no, my kid, she's 3, but she knows all about King Kong. They talk about him.
Very good, very good. I bet there is snow in New York, or at least a little bit.
Yeah. We hope so soon.
Very cool. Very good. And Parker, what do you like to do for research?
I like to work on instruments. So worked for a long time on the DESI instrument, what we're going to talk about today. And now I'm working on a calibration system for the up and coming Rubin Observatory that's based in Chile. And so we're building some of the hardware here in Tucson, and we'll ship it down to Chile. I also get to, now that DESI's up and running, I get to play with the data on DESI. So I've been working with some of the
Cool
stellar data coming off of the line of DESI and looking at stellar streams and really fun stuff.
Very cool. Very cool. So you're in Noir Lab, right?
I'm officially in Rubin Observatory, which will then transition into Noir Lab once the construction of Rubin's over.
Very cool. Okay, good. And Joe, what do you like to do for research?
I am the luckiest mechanical engineer you can meet, right? Because I work at Berkeley National Lab, and I get to work on just project after project that's
Nice.
In high energy physics and cosmology, robotics, alignment of really high power lasers, and just lots of interesting different areas. And it's not just the technology, which is cool. It gets your geek factor going, but it's just the people you get to interact with. I mean,
Absolutely.
Yeah.
I'm jealous. I'm gonna have to shift gears here. And that is going to bring us to this super awesome AJ article, the Robotic Multi-Object Focal Plane System of the Dark Energy Spectroscopic Instrument, DESI. And Joe and Parker, take us away.
Great. Well, thanks for having us. We are representing a huge group of people that help put together particularly the DESI focal plane, which is what we're going to talk about in this paper. But DESI, the Dark Energy Spectroscopic Instrument, is a collaboration spread out across the world, more than 20 different countries, and a growing number of collaborators. So it's a very international collaboration that has come together very efficiently and kind of put together this project that has been successful beyond our expectations. So we helped build this along with this great team, and we wrote this paper last year to kind of put together everything we did to put the focal plane together so that teams in the future who might be putting together multi-object spectrographs could learn from our success and challenges, lessons learned, and things like that. So we're happy to present this paper so that we can just grow this fantastic field and particularly improve upon multi-object spectrographs in astrophysics.
Very nice. Very nice. All right.
So DESI is an instrument and a project, both a survey rather, being operated out of Kitt Peak National Observatory, which is just down the road from Tucson on the Tohono O'odham lands. And the Mail telescope is in my opinion, the crowning jewel of Kitt Peak. It's a 4-meter telescope, sits right on top there, and DESI is mounted on the Mail telescope. One benefit that DESI has of being on a relatively smaller telescope, 4-meter, rather than 8-meter, 10-meter, kind of these ever-growing telescopes, is that DESI is the only instrument on the Mail telescope, and so we get all of the time. And so
Nice.
DESI is really a workhorse survey where every night we are working towards essentially one goal, and that goal is to map the large-scale structure of the universe. And the reason we are doing that and are interested in doing that is to help us better understand dark energy. Dark energy is maybe not a great term, but it is the term that's used more or less to explain the phenomenon of the acceleration of the universe. And so what we really want to do is understand how the universe has changed over time, so that we can understand if dark energy has changed over time.
Right. Good.
And so in order to do that, we need to look at the universe, both all around us, you know, in every location, but also back in time. And we can look at galaxies back in time because it takes time for light to get to us from those galaxies. So whenever you're looking at a galaxy that's very far away, you are looking at a galaxy very long time ago. And so we're able to use that to help us map out what the universe looks like over time. And so the goal is to measure the location of as many galaxies as possible, not only in their location on the sky as we see it, but also how far away they are from us, and how quickly away they're moving from us, their redshift. And so we can measure their redshift using a spectrograph. And so the Dark Energy Spectroscopic Instrument not only takes the light from all these galaxies, but then spreads it out so that we can look at all of the components of light from those galaxies. And with this information, we can start building up this 3-dimensional map of the universe. And we can start evaluating how far kind of the relationship between how far these galaxies are away from us to how quickly they're moving away from us. And that relationship right there helps us better understand dark energy. Because like I said, that's the term we use for the acceleration of the universe. And so we really want to understand, has the universe always been accelerating? Is it just accelerating now? And how has that changed over time? And so more data is better. And we're not the first instrument to ever try to go and measure a bunch of galaxies to do these kinds of measurements. We really are just the next step up from a lot of fantastic large-scale spectroscopic surveys. And the one that kind of came right before us was called BOSS. It was done on the Sloan Digital Sky Survey, a telescope in New Mexico. And what they did is they took big plates, big aluminum plates, and they actually drilled holes. And then they put fibers into each one of these holes. And then they already knew that the hole aligned with a galaxy. So they had done their research before. And then they put that on the telescope. And then they measured the light from the pre-drilled holes. And people did this, meaning the plates were drilled and then human beings would plug fibers into each one of 1,000 holes per pointing. And I can't believe they did that. That sounds exhausting. But when we talked about doing more fibers, more galaxies on every pointing, up to 5,000, which is what DESI has, the human factor is just not that's just not going to work. We're not going to be able, it's not a,
Doesn't scale.
it doesn't scale exactly. So we needed a new way to put fibers on galaxies.
Okay.
And so we use robots. And Joe was the main designer of the kind of robots that DESI uses, which we're going to talk a lot about here. But it really enables us to move 5,000 fibers onto 5,000 objects, mostly galaxies, sometimes stars. And then it stares at those for about 20 minutes. We get the light, send it to the spectrograph, spread it out, and then we shift to another part of the sky. And we can remove the fibers to align with them robotically. And so that's kind of a new step in this highly multiplexed spectroscopic instrument. And DESI is really the first to show this capability on such a large scale.
Yes.
And we're going to get into all the technical details because that's what this paper is about. But happy to say DESI's been installed for over a year now and is surpassing expectations with the number of galaxies that we've been able to measure. And our first data releases will be coming out soon. It takes about a year for each data to release to come out. And we're really, we have met all of our goals and expectations and even more so. So happy to say that it's been very successful, and so glad to share with others how we built it and how this thing works.
Well, I like happy papers, and this is a very happy paper so far. Everything is going fantastic.
Excellent.
Okay.
But yeah, let's start with figure 2. It's on page 4.
Thank you.
So you can kind of get a layout of what we're going to be talking about. So the pink line you see on the right there is the 4-meter primary mirror. And so this is going to be staring out into space. The light comes down, bounces off of that mirror, and then goes through the prime focus corrector. So DESI has 4 1-meter optical elements, really big pieces of glass, but that helps correct for chromatic aberrations and things like that. And then the light then lands on the focal plate assembly. So that's the back part. And that's what we're going to be talking about today. The focal plate assembly holds 5,000 fibers that are moved robotically. Now the light from those fibers then needs to get to spectrographs. And what you don't see here, and I think we probably have a plot or an image somewhere else, the fibers go down the telescope and down kind of into the basement almost of the telescope, kind of the base, and then go into spectrographs, where there are 3 different cameras spread out the light and image the light there.
Cool.
One other element I want to point out here is, in order to position the fibers, we have a fiber view camera, which looks at the fibers and confirms whether or not they're in the right place. In order to do that, we have to actually backlight the fibers. So instead of having light go down to the cameras, there's a light near the cameras that comes backlights those fibers. And the fiber view camera tells us whether or not they're in the right place. And then there's a feedback control loop where it says, nudge this fiber over a little bit, nudge it a little bit that way. And then we're able to align them within less than a hair with the location that we're going for. So that's an important element of this infrastructure. I'm going to say one more thing before we move on. We kind of have the DESI focal plane and spectrographs system. So we have the the focal plane instrument, the fiber system, and the spectrographs have been sliced into 10 unique subsystems or identical subsystems, really. So each subsystem includes what we call a petal of positioners, and the fibers from that one petal go in one fiber bundle to one spectrograph. So
Okay.
we kind of built the whole focal plane
Okay.
in 10 identical, more or less identical slices.
Okay.
And so you'll see next one of these slices, and kind of Joe will explain everything that's in that slice and then break down the individual components.
Cool. Very cool.
All right. So yeah, maybe you go up to figure 1, actually, and the,
I was looking at the figures part. Maybe we'll start at 3. I thought maybe we could build this thing from the inside out.
excellent.
Okay.
Yeah,
Right,
sounds good.
Yeah.
Figure 3.
Yeah. Yeah.
Okay.
Please go ahead. You're doing perfect.
Oh no, I want you to explain this positioner that you masterfully designed.
Yeah, believe it or not, that's my hand in that glove.
Awesome.
Yeah, that picture's gone through a lot of slide decks. Yeah, that's the fiber positioner, and you can see there's a little streak of sort of thin brown plastic running through up to the tip on the left of the robot. That's a thin polyimide tube around the actual optical fiber.
Okay.
Yeah. And so these things are long and skinny. I mean, you can see it's like almost 300 millimeters long, and it's because they have 2 degrees of freedom. They've got 2 tiny brushless DC motors in them that give you 2 degrees of freedom of motion.
Okay.
And there's a certain amount of mechanical complexity you need to build a robot. And since we're packing these things so tightly together, there's sort of like a Poisson's ratio effect of mechanical complexity. You just got to make it long and skinny and make everything long and just pack it all. Yeah, that picture on the right shows the 2 axes of motion. We've termed them theta and phi. There's a central axis, then an eccentric axis.
Okay.
Excuse me. So you can get that fiber to go on arbitrary points within a circular disk.
Right. Very cool.
Yeah. So let's go back up. Let's go from there. Actually, let's go down to figure 6.
Yeah.
Figure 6.
Yeah.
Really awesome.
We'll just keep kind of like building up this instrument and zooming out, I think.
Oh, I love this.
That one right there.
Yeah.
Oh, go back up a little bit.
6. Yep.
Right there.
Nice.
So now you can see a bunch of the robots right next to each other.
Cool.
And you're looking at a pretty close view because you can see like circles with little black dots in them.
Like here.
That circle is a glass ferrule that's only 1.25 millimeters diameter.
Wow.
Okay, these things are small, and that circle inside there is the fiber tip.
Yeah.
And so that fiber tip it's only 107 micron fiber core, 176 micron fiber. Anyway, it's small stuff. And you can see it. Yeah, please go ahead.
Yeah, help me get a sense of the image size here. So what is sort of a rough distance between the robots?
Yeah, the center to center spacing is on average 10.53 millimeters.
That's some precision.
Yeah.
Okay, thank you.
Yeah, I'm an engineer. If you hold one of these robots, I mean, you can see that picture for scale with my hand. I have normal sized hands, I would say. And so these things are about the size like a Sharpie marker.
Okay.
But a little bit longer.
Yeah,
and I think you can see how each one of them has that arm that we call the phi arm, which is making the eccentric motion, and then what you're seeing here is the sort of upper housing of it, and that whole upper housing rotates about the central axis.
Okay.
Yeah,
I'm with you. Very nice.
Okay.
It's beautiful.
Cool. And then let's go up to the pedal unit, which would be figure number 1.
Okay.
As we're kind of building this thing up from the inside out.
Sorry. There we go.
And this is what Parker was talking about, how,
Yeah.
this is what Parker's talking about, how he divided the instrument into 10 36-degree modules, each one called a pedal assembly.
Okay.
It's clear why you'd want to modularize these things. I mean, it's complicated, and you want to divide and conquer the problem, sort of, and have repeatable units where you have repeatable testing and integration. The reason for 10, which is kind of a strange number, is that we early on in the project decided on 10 spectrographs, and that was driven by CCD size actually, and how many fibers we could get across a CCD. And so those kinds of system level decisions happened very early, and we decided on 10 spectrographs. And once you got 10, you might as well make yourself have 10 petals so that it all just logically connects up.
Right. Cool.
And you can see that there's at the fiber tips in the upper right view, you can kind of work your way from where the light enters the fiber tips, and then the front of the robots, and then there's a thick aluminum plate, which is that black structure, which is supporting all those robots very rigidly. And then going back down, down through each of those robots has its own electronics board. Wow. And then the guides and for the many wires that are driving the electronics and the fibers. There's 5 wires per robot and a fiber per robot. So all that, we had to organize. It's kind of fun and take some time to figure out how to make it really logical and organized and planned. And early in the project, this area that you're looking at was often referred to as the nido de ratas, the rat's nest. Somebody came up with it, but anyway, we managed. It looks a little bit hairy there, but actually, when you get right up to it, it's pretty organized. And that was actually kind of a big deal, was to figure out how to just architect that. And
it's also just beautiful.
Thank you. Thank you, Frank. I think so too. I think it's gorgeous.
There's all the technical stuff, and then this is just it's a piece of art. It's beautiful.
Yeah. You get those black anodized structures next to, a lot of times you have that kind of gold chem film on aluminum parts, and you get the kind of black and gold effect. It's kind of nice.
Yeah. Very cool. All right. We are building this thing.
Okay. So let's move out. Let's see 10 of these things together. And for that, we're going to go all the way to figure 18.
Okay. I'm getting better here. 18. Ooh, lovely.
Yeah. Okay. It's a big paper. We tried to put a ton of interesting detail in there. For people who want to geek out and see what we were doing and go home and build one yourself, it might take a couple of years, but it's there.
No, I think this kind of exposition at this level of detail is really valuable.
Yeah, it would be good to get even more of this for every interesting instrument.
Every instrument.
Write it all down, which you did, yeah.
All right, so we got our 10 segments here.
Yeah, and this is actually this is a picture taken with the fiber view camera that Parker was talking about that can see, image the whole thing. And it's looking through the optical corrector.
Cool.
6 pieces of glass, and this focal plane is there. And then if you look in the upper right and lower right views, those are also from the same fiber view camera. So the left picture and the upper right picture are bright images where we turned on. We've got some lights that we can brighten it up so we can just see stuff. Okay. And then the lower right picture is where we turn off those lights, so it's dark and we're just backlighting the fibers. And that's where you can do centroiding measurements, which are super accurate. Some members of our group from Yale, David Rabinowitz, Charles Ball today, they've brought in really accurate 30 millipixel centroiding, very accurate stuff. And that's ultimately how we can be so precise. We often it's funny how we often communicate about things in terms of hairs widths, but I've heard hairs be 50 microns or 100 microns. I don't know how much a hair is.
Yeah.
These things are accurate to 2 microns. And it's all just driven by how well you can image it with the fiber view camera, because we got a big gear reduction on the motors, and the way we drive, they're very precise motors from Namiki Corporation, now called Orbre. But those motors are very precise, and we can be almost arbitrarily precise with our motions. So it's really just about how well we can survey where the fibers really are. And interpret, the optical distortions, the astrometry, and all that stuff, which is complex.
Yes.
Yeah. Okay. So I wanted to point out, while we're looking at that picture, in the upper right picture, that's a guide. We call that a GFA camera, guide, focus, and alignment. There's 10 of them on DESI. 6 of them are for guiding, and 4 of them are for the focus and alignment. We have a hexapod, so we can focus and align this thing at 6 degrees of freedom.
Okay.
And those were built by a consortium in Spain of several institutions in Barcelona and Madrid, led by IFAE.
Okay.
Yeah, and anyway, so that's what that thing is. There's 6 of those, 10 of those cameras.
Yep. Oh, yeah. Here we go.
And then the other sort of key part, we got the robots with the fibers, we got the cameras, which help you point and align and know where you're really looking on sky and that you're in focus. And then sort of the third key functional component is that next picture down. And that's what we call the fiducials. And these were also built by there's some collaborators at Yale who did the fiber view camera that I was talking about, Baltain Rabinowitz. And these, they present 4 little dots of light each, and we've surveyed really accurately where those are. Parker did, to the several micron level measurements of where every one of those dots is on the focal plane before we ever even installed it.
Okay.
And so those are your references that with every single image you can take out distortions and find where the fibers really are in true space on the FEC CCD, on the fiber camera CCD, because you're getting these reference dots along with the fiber. Okay, so that's the focal plane kind of summarized. And I think the last cool picture to take a look at is figure 16, just a few up.
Yep, give me one sec. Lost my cursor there. 16. Ooh.
Yeah.
Okay.
Okay, this is kind of neat because this is looking, there's these portholes around the side of the steel structure that holds the focal plane. So this is when we had 8 of the 10 petals installed.
Okay.
Those red things were they're like protective plates before we put in the other 2 petals.
Yeah.
So this is like during installation, and you're looking through this porthole, kind of a side view of the instrument. It's just a really cool picture.
Very cool.
And you can see the guide focus camera with the R-band filtered on it.
Very nice. Very nice. Cool.
Yeah, I think maybe one last thing. Well, not last. You can see it's a complex instrument. It's fun. You can talk about all kinds of corners of it. But why don't we go to? Oh, I lost my picture where I'm looking at the figure numbers.
All good.
But why don't we go to figure 5? Yeah.
Okay.
Figure 5. Okay. So this shows the performance of the robots.
Okay.
And so that's over a less than a month period. There's a couple of performance plots, but anyway, that's how they do. So we have kind of every time we retarget, we have a blind move and a corrected move, is what we call them. There's no encoders on these motors. It's just extra cost and complexity to put an encoder. The robot has no idea where it is. We're just spinning the magnetic fields on the 2 motors by a set amount. And there's no real torque variation or anything to worry about. It's just moving a fiber. Okay. So and it's a short move, so we don't actually care that much about how much power we use. It's just, we just apply what we've determined in the lab is a sufficient amount of current, and we just rotate these things rotate the magnetic field for each of these motors by a fixed amount.
Okay.
And that's what puts them on target. The first move is what we call blind, and so you can see it's about 50 microns accuracy. And the reason it's not dead on is like gravity deflections and slight variations between like the calibrated values for the robot's kinematic parameters versus reality, stuff like that.
Right. We're actually on it.
And then we do this one correction move. We take a picture of the fiber view camera, see where we really are, and then do this correction.
I mean, things such as temperature variations from one observation to the next can have effects on all this. So,
yeah,
well, that's a very good correction. I mean, you basically pile it all into 1/10 of a micron.
Yeah, it's just limited by how well we can
Yeah.
um,
Few
how well
microns.
we can image these things. There is turbulence in the dome that some very clever people led by Eddie Schlafly have reduced this error, I think even from, I think this one
Figure 4.
includes those fixes. Yeah, it was 9 microns before that, and they got it down to 6 microns error. And
So
these,
is that a physical change in the observatory that changes that turbulence, or
yeah,
you correct
yeah,
for the turbulence?
there's, I think it's something like 10 meters of air gap or 9 meters, something of air gap between the fiber view camera and the corrector. And
Okay.
so, just gentle plumes of air moving
Uh-huh.
through there. They move the backlit fiber images that we're trying to centroid on to see where the fibers truly are.
Okay.
So those little dots on the fiber view camera CCD are moving slightly around.
Okay. I'm with you. Thank you. Good.
Yeah.
Now, originally, and still, we allow for several repositionings of the fiber after the blind move, up to 3 repositionings. But one of the reasons why DESI is doing so well and kind of ahead of schedule on the survey, in part, are things like getting on target within 1 position.
Okay.
And many other things that people have worked on other subsystems, but cutting down on timing in everything has really pushed the survey ahead. So
Right.
these things really start to add up and matter.
Very nice. Okay.
Yeah.
Should we talk about any of the calibrations or early stuff? Software
So-
testing.
It's one thing that people always like to learn about a little bit or talk about a little bit and advance their own theories. A lot of people have good ideas, is the anti-collision. It's all these robots are packed close together and can hit each other. So we have software that makes them not do that.
Collision avoidance system.
Collision avoidance, yeah. If you go to figure 25, you can see it's kind of a neat picture. Wait till you get there. Yeah, there we go. Yeah. So all those ID numbers, M followed by 5 digits, are each a different robot's ID number. And we're just leaving the fiber view camera shutter open with the fibers back illuminated here.
Yeah.
And you can actually see the paths that they take. And there's kind of like an overlay of an arc that's drawn on there. But if you didn't have that overlay, you can also see little dashes on each of these arcs. Have a little bit of dash. And that's actually the PWM frequency of the LED that's lighting up the fiber. And then of course it's saturated where the fiber paused for a little while.
Yeah.
And so these funky arcs are done so that it's all pre-planned. Every single repositioning is pre-planned for all 500 robots on that pedal. And so there's a software model that quickly assesses all the best paths and then does it so that they all go where they want to go. And there's some discussion in the paper of how we do that. And collision avoidance it's one of those fun problems that the algorithm itself doesn't take any like real world knowledge, so like you can kind of just dive in. And what we found out in practice was that actually some of the hardest parts of it are getting the calibration right and the timing right, and those kinds of real world problems. But anyway, it is a fun subject. It's probably not something we need to like talk about how it really works here, but it's in the paper. Yeah,
in the paper, and it's a lovely visual.
Yeah, it gives you a real sense for what the robots are really doing.
Moving around. Yeah.
Okay,
very good. Okay.
So one thing that we focus quite a bit on the paper is just stepping through how things are built. You can kind of pause on figure 27.
Okay.
Just to look at that while I talk about this, I guess. But anyways, there are many parts to building up a positioner and the focal plane in general, because we talked about there's GFAs, there's fiducials, there's all the things to control the fibers, and there's a lot to it. The positioners were built at University of Michigan in several different steps. And I would say for astronomical instruments, both space and ground, almost always they're one-off instruments, right?
Yeah.
Which makes it very exciting to work on. But I would say that the community is not used to doing a lot of one thing, where we are not mass production organizations for the most part. And so it took a lot of planning and important attention to detail and kind of some identification of engineers who are more used to mass production of things to make sure that we had the QA in place, had good documentation, good testing, and all these things so that we could make 5,000 of a lot of different things that need to work very precisely. So that was something new for DESI, which certainly if someone does this in the future, they will have to pay attention to. So a lot of the positions were actually built by students at University of Michigan, not all of them. They also had kind of technicians hired at University of Michigan to complete this. But a big effort to put all this together and make sure that we had a quality quality components. Kind of if you buy it from a vendor, you just kind of forget about all of that. But we didn't have that luxury. So we needed to do QA on every single one of these positioners. And then once a full pedal was assembled, which was challenging, one of the interesting parts of the DESI instrument, I would say, is we don't have fiber connectors. So the positioners are inserted into the pedals from the front. It's a 3-meter length of fiber optic. And all 500 positioners for a single pedal would be installed. And then they would be fused to the rest of the fiber optic cable. And this fusion process is really a melting of two ends of the fibers. But this buildup of each one of the pedals took teams of 5 to 10 people after all the positioners had arrived. And then we had to test it and make sure all the positioners moved as expected. And there is a picture of,
take a look at that.
maybe let's stop first at figure 30 and kind of see the buildup of the positioners at University of Michigan.
Very nice.
And you can see actually building these positioners, it was a little slow, and then we sped up quite a bit towards the end, having to really incorporate these lessons learned and turn that around fairly quickly so that we could keep up the production level to high QA. And so, yeah, group of people.
Yeah, it's worth naming some names as well.
Oh, yeah, please.
I mean, that plot there is from Daniela Leitner, who is at Lawrence Berkeley Lab, and she was just essential in, taking possession of this this whole production and making it happen. Very closely working with Jessica Aguilar, a manufacturing engineer at LBL, who also was tremendous at doing this. At Michigan, the student and technician army was brought together by Greg Tarley and Michael Shubnell and Curtis Weaverdick, and it's pretty amazing what they brought together for a year and a half to make this happen.
Yeah,
and the students, people say they enjoyed it.
Valuable skill set.
Yeah.
Absolutely. So let me ask about the spares. So how many spares does one have now?
We built just over 7,200 robots.
Okay.
Yeah, we built 2 full spare pedals.
Yes. Okay.
Yeah. Yeah.
That's kind of what.
And we had a number of the robot motors fail in the instrument, not enough to harm the survey, but significant number, which we talk about in the paper. And yeah, so that was an interesting reality. So some of those spares may at some point come into play, but it costs time and money to replace anything.
Oh, absolutely.
Instrument's working pretty well and way faster than it was designed to work. So people say, let's keep running it.
Mm-hmm. What's a typical lifetime for one of those?
Well,
You expect it to last
over 1 million cycles, and
okay.
the number by cycle, I mean, of retargeting is what we tested it to, and what if you do the Weibull statistics curve, we thought these things would last 1 million cycles, but then reality interceded, and there turns out to be deep in these motors particular pinion gear, which was made out of a brittle material, and then a press fit which wasn't perfectly controlled at the factory, and has these micro cracks that can slip over time. So you don't find those micro cracks when you do a lifetime test of, let's run this thing for 1 million cycles.
Right.
You don't. There are things that grow over a couple of years, and so what we had happen. Oh yeah,
I wanted the crack picture. This one. Yeah, there we go.
Yeah.
There
So
we go.
they're very good motors, and I would not want anyone to come away with a picture that the manufacturer did not do. They did an excellent job. And the motors that don't have the crack are phenomenally accurate and reliable. But physics can be tough, and these ones were tough to pick up because you couldn't really find them at the factory. We couldn't find them in testing in the lab because it takes a couple of years for those cracks to propagate.
Yes. Mm-hmm. Mm-hmm. Cool.
But anyway, the instrument is it was a little bit of a scare moment, but the instrument is doing well. And right now these things develop at a rate of 1 a week, and that's been pretty steady.
Okay.
Everybody would, of course, always worry, and there's lots of study of the statistics we can get to see if that ever accelerates, because you wouldn't want to be on the accelerating side of a bathtub curve. But so far, if it's either linear or, if anything, decelerating the failure rate. But it's hard to tell when it's like 1 a week. It's tricky to see what the true rate is. So
okay.
Yeah.
Good. Thank you.
You put something together this complicated, and there's a lot of pitches, wild pitches that you dodge, and 1 or 2 that you don't. Yeah.
Some you miss and some you don't.
Yeah.
Yep. It's very good.
Yeah.
But you dodge enough of them.
Yeah,
It's working. Very good. Okay. Anything else we want to cover? Want to cover any of the software? You want to?
Before we go, I mean, there's a million things to cover, but I think we've covered a lot of the core stuff, but definitely want to call out a couple other main authors in the paper. Joe mentioned already Michael Shubnell. He was critical in building the positioners, and Kevin Fanning started out as a student of Michael Shubnell at University of Michigan, and then moved over to OSU as a grad student and worked significantly on the software to make this work. So he's the third author right there. Yeah. So want to call them out for really kind of bringing this together. And then everyone has been critical in this whole list of people, really. From the GFA team, Berkeley team, and Yale team are the people who really built the hardware, in addition to the people who supplied the parts. But to make it work, took an incredible group of people to actually make the whole system work as we expected.
Right. Take that large complexity, divide by the number of authors, you have a very large complexity per author.
That's right.
To address. It's very cool.
Right. That's right.
Very cool. All right. Anything else you want to cover? Are we good?
I think that's pretty good.
Okay.
Yeah, I mean, I recommend people if they're interested in. Joe put together a really terrific lessons learned section. So anybody who watches this who might be thinking about making their own system, take a look at our lessons learned section, because we really wanted to build something for we're trying to be very open about what we did struggle with. We really want to share that so that we can all grow together as a community of instrument builders. Yeah,
absolutely. Yep.
Yeah, and I think on that note, I would, say I really appreciate, the Astronomical Journal in taking this paper on, and we have a number of instrument papers of this kind of length and depth. We've got, I think, 5 of them for DESI.
Okay.
Really exploring the, the spectrographs and the fibers and the overview of the instrument. And anyway, AJ's really given us a forum to put all this information in a place where everyone can see it.
Awesome.
I think that's a really good thing that the journal did. Personally.
Well, I'll take that shout out. Okay, very good. Thank you. You can keep waxing on for the next 10 minutes on that topic.
It's not exactly a traditional astronomy paper, but it's something that the community, I think, wants to see.
I would totally agree. I mean, on the other side of the house, there's software instrument papers, right? It can be just as complicated in a software instrument as hardware. We definitely publish software instrument papers, usually in the APJ supplements. And so we should very definitely be doing this level of depth in the hardware instrument side as well. So I'm glad that the journals is taking on both of those, hardware and software instrumentation. So very cool. And here it is. There is the mail. On a good day, on a sunny day. Very cool.
Yeah.
Joe and Parker, I want to thank you so much for walking us through this very awesome instrument. Yeah, thanks.
Thank you.
So let me ask, so the instrument is built, the instrument is on the telescope, it is producing data, soon we'll have data releases. And so let me ask, where do you go from here with regards to the robotics and the construction of the instrument itself? Will there be a version 2? Is there a DESI 2.0 camera?
People
or does the technology get implemented onto other telescopes? So just sort of where do we go with this over the next couple of years, let's say?
David Schlegel, who's I would say one of the driving forces between over the decades pushing these instruments again and again to the next level, has a plot that he often shows of how this multi-object spectroscopy has increased in scale over the years, kind of like those like Moore's law plots you see.
Yeah.
But there's no law to say that it has to happen. You got to make it. And so there's a lot of interest, especially seeing how DESI, how well it's worked. There's a lot of interest in going to the next step of scaling. There's people who talk about using the DESI corrector but adding more spectrographs, shrinking the robots even smaller than they are, and maybe about doubling the number of robots on DESI. That's one discussion. There's also discussion, there's plenty of discussions in the community about different ideas for multi-object spectroscopy. One of them that's gotten a lot of interest takes essentially the spirit of the DESI robots, shrinks them again, but builds a new maybe 6-meter telescope or so and gets like 25,000 robots. So we're in this state where we're not sure like exactly, is it going to go towards like maybe 11,000 robots or like 25,000, that kind of scope. But anyway, trying to multiply done by a factor of 2 to 5, I think is where people are aiming right now.
Nice.
Yeah.
Very cool.
Yeah. And we with the collaborators at École Polytechnique Fédérale de Lausanne, EPFL in Switzerland, Jean-Paul Kneb and his group, they were deeply, we didn't mention their name, but they were deeply involved in the DESI robots, as they were deeply involved also in the SDSS-5 robots, which is an instrument that just came online. And so I know that our Berkeley group has been working a lot with EPFL on we're working on sort of shrinky dinking these robots and making the next generation, which it'll be about 2.5 or 3 times more dense,
Right.
about 3 times more dense. And that'll be an enabling technology. And if people are out there who are interested in getting involved in this stuff, we're trying to build up another sort of working group to get this to happen.
Okay. There's a job ad. Go for it, people.
Bring your own money.
There you go. Awesome. Joe, Parker, I want to thank you so much again for walking us through your very lovely article on DESI. Thank you.
Thank you.
And that'll do, everyone. And I hope this made your astronomy day just a little bit better, and we will see you on the next one. Bye-bye.